This video is meant to accompany ME366 Project 2 for fall of 2016. During class we've discussed with this project that what we're trying to do is we're going to let this entire joint be fixed on the left hand side, and we're going to put a 100-pound force on this panel right here pulling straight out. And what I want to do in this video is to show how to do that and some issues that come up along the way and how to overcome them. So I've got my part drawn. I'm ready to go into Study Advisor, and I'll do a new study. And I'm going to call this study Demo just to keep it apart from other studies that I've done in this part. And as we discussed in class, the part is finished up here. We've already assigned the material, and so if I look through, I'm going to see it's a solid body. I'm going to see that the connections are considered compact, are considered bonded, and we're ready to set up our fixture. So I'll right click on fixture. We're going to do a roller slider fixture on this left side. I'll click the check mark. And then for an external load, I'm going to right click and do a force on the right side of English 100 pounds and reverse the direction and check. So there's a 100-pound force acting on one side and a slider joint on the other side. If I look at my mesh options, they're set right in the middle right now. So create mesh, they're set in the default location. I'll click the check mark and create them there just for this demo, and we're ready to run this study. I get this message that says there are excessive displacements. If I click yes, I'm going to consider the large displacement option. If I click no, I'll continue doing it as the small displacement. I'm going to click no for now. We can always change that later. And you can see that we've got a von Mises of 25 KSI. I'm going to record that. So our stress is 25. That wasn't KSI, that was MPa, megapascals. And then we have a displacement. Let's click on the displacement here. And notice what this displacement is showing. It's showing that the beam twisted. It's a really odd shape. And this is one of the problems with the sliding joint. So the sliding joint solved one problem. It solved singularities that were occurring on the boundary conditions right there on the edges that ended up being spikes. But in order to do that, it relaxed a constraint. That's why we saw large displacements. And if you look at the displacement, it's in millimeters. I want to change it to mil because that's what I'm used to looking at. So this is 469 mil, or almost half an inch. It fell away from its original location and bent some. I'm going to write that number down. And then I'm also going to set up a new category, and you're going to need to do this in your projects as well. So on results, I'll right click, and we're going to define a new displacement plot. I want it to be mil, and instead of considering the total resultant displacement, I'm only going to consider displacement in the x direction, so the x displacement. The reason I can do that is the whole point of this study is to really understand how this part is being stretched in the x direction. I understand that I'm making some assumptions about the boundary conditions on the right that's allowing all that sliding to happen, and that's all okay because what I'm most interested in is what's happening here at the corner. Notice that now becomes 0.561, we'll call it. So let's come back here. .561 mil, and that's my first run here. So I have my stress value, I have a resultant displacement, a total displacement, and then I also have just the x displacement. Coming back to the study now, I'm going to just run again. I'm not changing anything at all except for running the study again. And again, I'll choose no. And if we look here at the von Mises, we're still going to get the 25, so that value is still the same. So for run 2, I'll still get 25 MPa. But if I look at the displacement graph, it still looks similar, except for this time it curved on, actually it curved on exactly the same way. Looks like I might even have the same value. And then for the second displacement, this number is also going to be the same. So all three of these numbers were the same. 469 mil and 0.561 mil. Justify everything together. There we go. And let's run it again. This time I'm getting very consistent results with this displacement, but it's kind of random that it's occurring that way. So if I look at, for instance, another graph, here's another small displacement. This is the same thing that was done, just done earlier. It's also showing that strange curve. If I consider large displacements, notice what it's doing. Its displacement looks very different. And if I run this one again, so no changes whatsoever, notice that up here in the top corner, it's red, and then going to blue down there at the bottom, and it's not linear. In other words, it's not the same all the way across the part. This has a displacement of 5 mil, 5.8 mil. If I run it again, the large displacement calculator takes longer. But notice the shape of displacement might vary, and it has a very different. Now it has 14 mil as the displacement. So it's going to be all over the place. So depending on what you decide to use when you do the demo, when you run your study, when I click run, if you choose no, so you use the small displacement calculator, even though large displacements are detected, you'll get a consistent result. You'll continue to get this 469 mil of displacement, which is completely unreasonable. If you only consider the displacement in the x direction, you'll find using either the large or the small displacement a very consistent result of 0.561 for the basic model. That should be what you expect your value to be for the blink, and that provides the pattern for the rest of the study.